Stanford University.
The biggest problem that people think of with arsenic is actually in Asia, where somewhere on the order of maybe a sixth of the groundwater in the continent is contaminated. So within the US, our work has focused mostly on Orange County, which is in Southern California. And there we look at their water treatment system, where they take recycled water, run it through then a very advanced treatment system, and finally take that water and use it as groundwater replenishment. And as that water percolates down into the groundwater, it picks up arsenic. Not high levels, particularly compared to Asia, but enough arsenic to move it above the drinking water standard.
We always knew this was a potential thing we needed to have our eye out for. That putting this really highly purified water back into the environment, what's going to happen geochemically when you do that. So we had a monitoring program set up at the onset of the project to really try to look at that closely. And we got some initial data on it that showed some small kind of transient increases. Our initial data says this doesn't really tend to persist as you get farther away, but as we sort of up the amount of recycled water we put in a certain area or look to put the water in new areas, we kind of want to have more certainty that it wasn't going to persist other places where we choose to apply this water in our groundwater basin. We really need to do a controlled study in the laboratory where we can control some of these environmental factors and really understand what's happening.
So there are a number of different ways that arsenic can be triggered to move from the solid phase into the water. One of the most pronounced ways is a shift in pH. So if you have a very high pH, arsenic will often destabilize from the solids and move into the aqueous phase. That's something you see in South America quite commonly. Another trigger, and probably the most pervasive, is moving from aerobic to anaerobic conditions. So in other words, a lack of oxygen. And that's what you see in South Asia, where we study the massive arsenic problem there. Third mechanism is that if you have an ion that's similar to arsenic, like phosphate, it's an analog and it can compete for binding sites. So arsenic is bound up on minerals. If you have an ion that's similar to that and in high concentration, you could displace it off the minerals and cause it to go into solution. So they ruled out all of those normal triggers for arsenic release. And that left them puzzled then, what was causing the arsenic to come into solution? And our job was to come in and figure that out. They had done a lot of work already on both the aquifer chemistry as well as the infiltration system. And they had collected sediments. What we did with them is to try to identify where would be the source of arsenic within the sediment strata. And by doing that, we carefully went through 162 feet of material to figure out if there were any high arsenic lenses in there. And there were lenses that were higher arsenic, little strata that had a little bit higher arsenic, but still quite low by global standards for sedimentary basins. We then set up simulated infiltration systems where we pack long tubes that we just think of as columns. We take water then from Orange County Water District, and we then percolate that water through these columns to understand how arsenic is being released and the concentrations that are being released. And then we go and we start modifying the water chemistry. So what we ended up identifying was that in effect their water is too pure. So the arsenic would be bound to the sediments. It's actually on the outside of these minerals, and it's bound in a fairly weak form. And it turns out that some of the arsenic needs calcium and magnesium to be retained on the mineral surface. And so as this highly purified water comes down percolating through the sediments, the calcium and magnesium then come off and replenish that water with calcium and magnesium, and the arsenic comes off with it. And so the solution to the problem ultimately then is to modify their infiltrating water so that it has higher calcium magnesium concentrations to match the natural infiltrating water.
We've altered some of our post-treatment operations here. We keep a closer eye on the calcium target and have actually increased that and boosted that recently. In part due to the recommendations coming out of Scott's work.
Groundwater replenishment systems are increasingly becoming common as we start thinking about how to increase our water resources, and particularly with moving towards subsurface storage. So instead of having to build surface dams and have these big infrastructures, we can start thinking about having water percolate into underground areas where we have capacity to store water. But what we recognize is that we have to be very careful about thinking of the geochemistry and alterations to the water chemistry that may trigger release of contaminants. We're going to see, as we increase groundwater pumping, as we try to think about innovative ways for groundwater storage, that these type of contaminants continue to pop up, whether it be chromium or uranium or arsenic. All those are elements that we're going to have to be concerned about, and things that are going to have broad implications from our work here.